bond energy calculations for Cambridge iGCSE Chemistry. So the overview, we'll start with enthalpy change, the idea of bond energy, and then calculations involving bond energies. Enthalpy change delta H. Reminding us of the reaction pathway diagram and the new idea that chemical energy is known as enthalpy and given the symbol H. So we have enthalpy of the system, the enthalpy of the reactants, and the enthalpy of the products are different. Is a reaction pathway curve, and of course the activation energy, which isn't directly relevant to our current lesson. The transfer of thermal energy during a reaction, that is the difference between the enthalpy of the reactant and the enthalpy of the product, is called the enthalpy change, and that is given the symbol delta H, delta for change and H for enthalpy. And that, of course, is the difference of the enthalpy value for the reactants and the enthalpy value for the products. We indicate on a diagram with a directional arrow from reactants to products, and we label that arrow delta H. Delta H for an exothermic reaction is negative. So an exothermic reaction, the reactants have more enthalpy than the products. So the change from reactants to products is a negative change. So delta H is negative for exothermic reactions. Now, for a reaction in which the products have greater enthalpy than the reactants, that is an endothermic reaction, delta H is of course positive. To move from reactants enthalpy value to products enthalpy value, we have to increase delta H. There's an increase, so delta H is positive for endothermic reactions. Every covalent bond has a bond energy value. That bond energy value is defined as the input of energy required to break 1 mole of the bond. So that is an endothermic process and it is given a positive sign. Here are some examples. The carbon-hydrogen single bond, 413 kilojoules per mole. Oxygen-hydrogen single, 467. Hydrogen-hydrogen, 432 kilojoules per mole. Oxygen double bond oxygen, 495 kilojoules per mole. Carbon double bond oxygen, 745. In breaking those bonds, the energy change is given a positive sign. It is an endothermic process. So when a bond is made, the opposite is true. Energy is released. It is an exothermic change, and therefore the energy change is given a negative sign. We can think of a chemical reaction as taking part or place in 2 steps. The first step being the breaking of bonds in the reactants, which is endothermic and absorbs energy. The second step would be the making of the bonds in the products, which is exothermic, releasing energy. If we look at a reaction pathway diagram, we can see that the first step, which is endothermic, is to break bonds, and then the second step, which is exothermic, is about making bonds. So that is true for an exothermic reaction. It's also true for an endothermic. We're going to break, and then the exothermic process is to make. So I'm going to model a bond energy calculation. Calculate the enthalpy change delta H for the reaction between hydrogen and chlorine to make 2 moles of hydrogen chloride. So the enthalpy change is going to be the energies of the bonds that are broken minus the energy of the bonds that are made. We put a minus sign in front of the bonds made because making bonds is exothermic, releases energy, and is given a negative sign. We put a positive sign in front of bonds broken because that is an endothermic process. So it has a positive sign in front of the energy values. So positive energy values for bond broken, negative energy values for the bonds made, which we achieve by putting a negative sign here in front of the value of the bonds made. So we've got a hydrogen-hydrogen and a chlorine-chlorine, and then 2 hydrogen-chlorine bonds. Remember, bond energies are per mole. So we've got 2 moles of hydrogen chloride, so 2 moles of the hydrogen-chlorine bond. Evaluate those from the table on the previous slide. 432 plus 242 minus, because the energy is released, 2 times 427. We sum all of those together, it comes to minus 180 kilojoules per mole. The enthalpy change is minus 180 kilojoules per mole. That means that more energy has been released. The sum of these bond energy values here, is greater than the energy absorbed in breaking the bonds in the reactants. So this summing these bonds is less than the sum of 2 times the hydrogen chlorine. So therefore, the reaction is exothermic. The reaction is exothermic because more energy was released in making the bonds than was absorbed in breaking the bonds in the reactants. So here is a problem for you to try. Calculate the enthalpy change for the reaction between hydrogen, oxygen to make 2 moles of gaseous water. Here are the necessary bond energies. Select those that you need. Carry out the calculation. Come back to check and correct when you are ready. Okay, so I'm going to reveal. The first thing to do is to analyze what bonds need to be broken. Well, we've got a hydrogen single bond hydrogen, but twice, an oxygen double bond oxygen, and then hydrogen, oxygen, oxygen, hydrogen. We've got 2 oxygen hydrogen bonds in a water molecule, but we've got 2 water molecules. So the bonds that need to be broken, 2 times the hydrogen hydrogen comes to 864. We take 432 as the value for the hydrogen hydrogen, and then the oxygen double bond oxygen 495. We total that and give it a positive sign, 1359, positive. We now look at the bonds that are made. Well, because there are 2 molecules of water and each molecule has 2 oxygen hydrogen bonds, in total on the right hand side we have 4 times the oxygen hydrogen. So 4 times 467 comes to 1868. But we give that a negative sign because we are making bonds which releases energy. The overall change, therefore, the enthalpy change is plus 1359 minus 1868, which comes to minus 509 kilojoules per mole. This, of course, is exothermic because it has a negative sign. More energy was released on making the bonds in the product than was absorbed in breaking the bonds in the reactants. So here is a second problem. Calculate the enthalpy change for the reaction between methane, oxygen to form carbon dioxide and 2 molecules of gaseous water. Now, the first thing to you're obviously using these bond energy values. The first thing to do is to analyze what are the bonds present in reactants and products. I may give you an assist on that just so that we are focusing on the bond energy calculation aspect. So there is methane, there is oxygen, double bond oxygen. So in O2 we've got oxygen, double bond oxygen, there's 2 oxygens. Carbon dioxide is carbon double bond oxygen, carbon double bond oxygen, and then we've got 2 molecules of water. So as on the previous slide, we've got to multiply the bonds within water by 2. Okay, having given you that assist, would you like to pause the lesson and complete the calculation, then come back to check and correct when you are ready? Okay, so I'm going to reveal the bonds broken. I've got carbon, hydrogen 4 times, which comes to 1652. I've got oxygen, double bond oxygen twice, because there's 2 molecules of oxygen. So 2 times 495 comes to 990. My total is 2642. I give it a positive sign because we are breaking bonds, which is endothermic. I now move to the bonds that are made. Got 2 carbon double bond oxygens, and then 4 oxygen hydrogens. Sum and give a negative sign because making bonds is exothermic. The overall enthalpy change is plus 2642 minus 3358. Again, it is exothermic. The enthalpy change is negative and therefore is exothermic. More energy was released on making the bonds in the products than was absorbed by breaking the bonds in the reactants. This particular topic really does need practice problems, so find some in your textbook or online. Make sure you've got access to answers. Then try past paper questions from Cambridge iGCSE papers. Thanks for watching. Please like, please subscribe, or most particularly, please recommend to a friend.